Hey everyone, and welcome back to the Deep Dive. If you love these deep dives into all this fascinating stuff, don't forget to hit that like button, subscribe to the channel, and ding that bell icon so you don't miss out. Today we're going to explore something truly fundamental to life on Earth, and, it connects us all in ways you might not even imagine. We're talking about biogeochemical cycles.
Yeah, these cycles are, they're not just some kind of abstract scientific concept. It's like they're the very lifeblood of our planet.
Wow.
Just imagine the Earth as this giant bustling city and all these cycles. They're like all these intricate transportation systems that just keep everything running smoothly.
Okay, yeah, I'm hooked already.
Yeah.
So we're talking about the air we breathe, the food we eat, even the rocks under our feet, all interconnected through these massive invisible systems.
Absolutely. And what's really fascinating is that these cycles are not just static. They're dynamic systems that are constantly in flux, always changing, being influenced by just a ton of different factors.
Okay, so let's unpack this a bit. We've got two main types of cycles, right? Gaseous and sedimentary.
Exactly. You can think of gaseous cycles as having their headquarters up there in the atmosphere, like this giant atmospheric warehouse. But the sedimentary cycles are a bit more grounded. They're mostly stored down there in the Earth's crust.
Okay, so like carbon dioxide just kind of floating around in the air versus something like phosphorus just locked away in rocks.
Exactly. So let's start with the gaseous cycles. Those elements and compounds that are constantly on the move up there in the atmosphere. And I think there's no better place to start than with the carbon cycle. It's kind of the ultimate poster child for interconnectedness.
Yeah, the carbon cycle seems to be in the news all the time these days, especially with everything going on with climate change.
Yeah, and for good reason. This cycle is absolutely fundamental to life as we know it. I mean, think about it. Every breath you take, every bite of food you eat, it all involves carbon atoms that have been cycling through this planet for millions of years.
Wow, yeah, that is pretty mind-blowing when you think about it like that. So how does this grand carbon cycle actually work?
Okay, picture this. Plants, they act like these tiny little carbon capture factories, and they're pulling carbon dioxide straight from the air through photosynthesis, and they use it to build up their tissues. Then the animals come along, right? They munch on these plants, take in all that carbon, and incorporate it into their own bodies.
Okay, so far so good.
Eh.
So plants capture the carbon, animals eat the plants, then where does the carbon go?
Well, both plants and animals release carbon dioxide back into the atmosphere when they respire. It's that process of breathing and breaking down food for energy. And then when organisms die, the decomposers like bacteria and fungi get to work, and they break down all those remains and release even more carbon dioxide.
So it's like this giant game of pass the parcel with carbon atoms constantly getting exchanged between the atmosphere living organisms and the soil.
Precisely. And for millennia, this cycle has been, beautifully balanced, keeping the concentration of carbon dioxide in the atmosphere pretty stable. But here's where things get a little tricky. Human activities like burning fossil fuels and deforestation have really tipped the scales.
Right, we're pumping way more carbon dioxide into the atmosphere than the natural cycle can handle.
Exactly. And all this excess carbon dioxide, it acts like a thick blanket. It traps heat, and that leads to a warming planet. And that comes with all sorts of consequences, like rising sea levels, more extreme weather events, and it's even changing where plants and animals can live.
Yeah, it's a pretty stark reminder of how interconnected we are with these cycles and how our actions can have these ripple effects throughout the planet. But let's move on to another key player in the atmosphere, nitrogen.
Ah, nitrogen, the element that makes up something like 78% of the air we breathe. But here's the catch. Even though it's all around us, most organisms can't actually use nitrogen directly from the atmosphere.
Really? That's kind of strange.
Yeah.
If it's so abundant, why does it need a whole cycle?
That's where it gets really interesting. You see the atmospheric nitrogen, it exists as this really stable molecule. It's like two nitrogen atoms clinging really tightly to each other. To be useful for life, though, that nitrogen has to be fixed or converted into a more reactive form.
So it's like nitrogen is speaking some language that plants and animals can't understand, and it needs to be translated.
That's a great analogy. And guess who the master translators are? Tiny microorganisms. Certain bacteria have this incredible ability to convert that atmospheric nitrogen into ammonia, and that's a form that plants can readily absorb.
So these bacteria are like the key to unlocking nitrogen's potential for life.
Exactly. This process is called nitrogen fixation, and it's that crucial first step in the nitrogen cycle. These nitrogen-fixing bacteria, well, they can be found in all sorts of habitats, from the soil to the ocean, and they play an absolutely vital role in supporting life on Earth.
Wow, these little organisms are like the unsung heroes of the planet. But what happens to the nitrogen once it's been fixed?
Well, it enters the food web. Plants absorb that ammonia, then animals come along and eat the plants taking in that nitrogen, which is super important for building proteins, DNA, and all sorts of important molecules.
Where nitrogen travels up the food chain just like carbon?
Exactly.
No.
And just like with carbon, eventually that nitrogen is returned to the soil through waste products and, the decomposition of dead organisms. But the story doesn't end there. Other bacteria get involved and they convert the ammonia into nitrites and then nitrates. And that's another form that plants can use. And finally, you have these denitrifying bacteria, and they complete the cycle by converting the nitrates back into atmospheric nitrogen. They just release it back into the air.
So it's this continuous loop of nitrogen transforming and circulating between the air, the soil, and all the living organisms. It's like a complex dance with different bacteria playing different roles.
Exactly. It's this intricate dance that is essential for maintaining the balance of nitrogen in the environment, ensuring that there's enough available for all forms of life.
Okay, I'm starting to see just how intricate and interconnected all of these cycles are. Now let's talk about another gas that we can't live without, oxygen.
The oxygen cycle. It's intimately tied to your every breath. The vast majority of oxygen is produced through photosynthesis, by plants and some microorganisms. And then this oxygen is consumed by animals and microbes during respiration. It's like this beautiful cycle of give and take.
So basically plants are our oxygen factories.
Precisely. They're constantly replenishing the oxygen in the atmosphere, making sure that we have all the air we need to survive.
But what about the water cycle? That one seems pretty straightforward, right? Evaporation, condensation, precipitation.
You're right. The water cycle is something that we're all pretty familiar with. But what people often overlook is how this continuous circulation of water in all its forms connects this entire planet. From the oceans to the atmosphere to the land and then back again, water acts as this vital link in Earth's grand system.
Okay, so we've covered all the gaseous cycles. Now what about the elements that are mostly locked away down there in the Earth's crust? The sedimentary cycles, right?
Yeah. Now let's shift gears a little bit. Let's delve into this realm of sedimentary cycles. And these cycles, they're a little different from their gaseous counterparts, you see. They involve elements that are mostly stored down there in the Earth's crust, and they move at a much, much slower pace.
So it's like a slow motion version of the cycles we've been talking about.
Precisely. And one of the most important sedimentary cycles is the phosphorus cycle. Phosphorus is a really critical element for life, It plays a key role in DNA, energy transfer, and all sorts of other essential cellular processes. But unlike carbon or nitrogen, its primary reservoir isn't the atmosphere, it's actually rocks.
Oh, wow. Okay. So how does phosphorus get from rocks to living organisms then?
Through a process called weathering. As rocks are exposed to the elements, wind, rain, temperature fluctuations, they slowly break down. And that releases small amounts of phosphorus into the soil. Then the plants, they absorb this phosphorus through their roots, and then it continues up the food chain as animals eat those plants.
Wow, it's amazing to think that even rocks, seemingly so inert and unchanging, are actually participating in this grand cycle of life.
It really highlights how interconnected everything is on Earth, doesn't it? And this slow release of phosphorus from rocks is why it's often a limiting nutrient in ecosystems. That means that plant growth can actually be restricted by how much phosphorus is available.
So that's why phosphorus is like a crucial ingredient in fertilizers.
Exactly. Because its natural release from rocks is such a slow process, farmers often supplement the soil with phosphorus-rich fertilizers, just to make sure there's enough for the crops to grow.
It's fascinating how understanding these cycles can actually inform our agricultural practices.
Yeah.
But too much of a good thing can be a problem, right?
Oh, you're absolutely right. While phosphorus is essential for plant growth, excessive use of fertilizers can actually lead to runoff into waterways, and that causes a whole cascade of issues.
What kind of issues?
Well, when excess phosphorus enters lakes and rivers, it can trigger excessive growth of algae. It's a phenomenon known as algal blooms, and these blooms can deplete the oxygen in the water, harming fish and other aquatic life.
So it's this delicate balance then.
Mm-hmm.
We need phosphorus to produce food, but we have to use it responsibly, or we risk disrupting the aquatic ecosystems.
Precisely. It's all about understanding this interconnectedness of these cycles and finding ways to manage them sustainably. Now let's turn our attention to another key player in the sedimentary realm, sulfur.
Sulfur. It always makes me think of volcanoes and that rotten egg smell.
Oh, there's a good reason for that. Volcanic eruptions release a significant amount of sulfur into the atmosphere, but sulfur is also an essential element for life. It plays a vital role in the formation of certain amino acids, which are the building blocks of proteins.
So sulfur is like this globe-trotting element traveling through all these different parts of the Earth's system.
Precisely. It cycles between rocks, water, the atmosphere, and living organisms. And here's an interesting twist. Remember how we talked about acid rain in the context of nitrogen? Well, sulfur plays a role there too.
Okay, remind me how that works again.
When sulfur dioxide, released from volcanoes or industrial activities, enters the atmosphere, it can react with water vapor, and that forms sulfuric acid, and that contributes to acid rain.
Right. Acid rain can be harmful to forests, lakes, even buildings. It's like this chain reaction of unintended consequences.
Exactly. And this just highlights how important it is to understand how human activities can actually disrupt these delicate cycles and find ways to minimize our impact. Now, before we move on, let's take a step back and talk about the rock cycle itself.
Okay, how does the rock cycle fit into all of this?
The rock cycle is like this grand overarching process, and it drives the release of many elements, including phosphorus and sulfur from rocks. It involves the constant transformation of rocks through weathering, erosion, sedimentation, and metamorphism.
So the rock cycle is like this maestro orchestrating the release of these essential elements for other biogeochemical cycles to play out.
Exactly. It's the foundation upon which many other cycles are built. And this interconnectedness, it highlights the complexity and beauty of Earth's systems.
It's truly mind-boggling to think about how these cycles operating over these vast time scales and spatial scales are all interconnected, and they're all essential for life as we know it. But it's not just about these cycles operating in isolation, right? There are other factors at play as well.
You're spot on. These cycles are constantly being influenced by all these environmental factors that shape their dynamics and impact their flow.
Okay, let's dive into that. What kind of factors are we talking about?
Well, for starters, soil characteristics play a huge role. Think about it. Different soils have different textures, compositions, drainage properties, all of which can impact how nutrients are retained, released, and absorbed by plants.
So it's not just about having soil, it's about having the right kind of soil for the job.
Exactly. For example, sandy soils, they tend to drain really quickly. So that means nutrients can be leached away pretty easily. But clay soils, they hold on to nutrients much more tightly.
So it's like different soils have different bank accounts for nutrients, some with high interest rates and some with low interest rates.
That's a great analogy. And then there's moisture. Adequate moisture is crucial for microbial activity, and that drives a lot of the processes involved in nutrient cycling, like decomposition, for instance.
So too much or too little water can throw things off balance.
Absolutely. Drought conditions can slow down nutrient release, while waterlogged soils can lead to a buildup of certain compounds that can actually be harmful to plants.
It's all about finding that sweet spot.
Yeah.
Now, what about pH? I know that's a measure of acidity or alkalinity, but how does it impact these cycles?
pH plays a critical role in nutrient availability. Different nutrients have different solubility levels at different pH levels. So, for example, in acidic soils, certain metals like aluminum can become more soluble and potentially toxic to plants. But in alkaline soils, it can be harder for plants to absorb essential nutrients like iron.
So it's like the soil's pH is its personality. It can really affect how nutrients behave. And what about temperature? I imagine that plays a role too.
Temperature is a major factor. As a general rule, warmer temperatures speed up biological processes. That includes decomposition and nutrient cycling. But colder temperatures, they slow things down.
So in a way, temperature acts like a thermostat for these cycles, speeding them up or slowing them down. It's incredible how all these factors just intertwine to create this delicate balance.
It truly is. And it highlights the importance of understanding these cycles, not just in isolation, but in the context of the larger environment and all the myriad factors that can influence them.
Okay, so we've covered the types of biogeochemical cycles, the elements involved, and the environmental factors that can influence them. But let's bring it all home now. Why should we care about all of this? What's the big deal about biogeochemical cycles?
That's the fundamental question, isn't it? And the answer is simple. Biogeochemical cycles are the foundation of life on Earth. They're the mechanisms that ensure the continuous supply of essential elements and compounds for all living organisms.
So it's not just about these pretty cycles. It's about the survival of life itself.
Exactly. These cycles provide the building blocks for everything, from our DNA to the air we breathe to the food we eat. Without them, life as we know it simply wouldn't exist.
It's a powerful reminder of how interconnected we are with this planet and how these seemingly invisible processes are absolutely essential for our very existence.
And it goes beyond just survival. Biogeochemical cycles play a crucial role in regulating Earth's climate, particularly the carbon cycle, which influences greenhouse gas concentrations. They also contribute to soil fertility, which is essential for agriculture and food production.
So understanding these cycles isn't just some academic exercise.
Yeah.
It's crucial for addressing some of the biggest challenges facing humanity, like climate change and food security.
Precisely. By understanding how these cycles work, how they're interconnected, and how human activities can impact them, we can make more informed decisions. Decisions about how to manage our resources sustainably and protect this planet for future generations.
It's a call to action for all of us to become more aware of our role in these grand cycles and to act responsibly to ensure their continued balance.
Well said. And that brings us to another fascinating aspect of biogeochemical cycles, their role in shaping the very landscapes we inhabit.
Okay, let's explore that. How do these cycles influence the physical world around us?
One of the most striking examples is the role of weathering in shaping mountains, valleys, and coastlines. That constant exposure to wind, rain temperature fluctuations, it gradually breaks down rocks. It's a process that releases nutrients for other cycles, but it also sculpts the landscape over millions of years.
So the majestic mountains we admire are actually products of these ongoing biogeochemical cycles.
Exactly. And it's not just about weathering. The movement of water through the water cycle, for instance, it plays a crucial role in carving out riverbeds, forming canyons, and transporting sediments that build up deltas and coastal plains.
It's like nature's own construction crew constantly reshaping the Earth's surface.
Precisely. And even seemingly insignificant organisms play a part. For example, lichens, those colorful patches you often see on rocks. They actually contribute to weathering. They release acids that slowly dissolve the rock surface.
It's amazing to think about how even the tiniest organisms can have such a significant impact over time. But how do these cycles play out in different ecosystems? Are there variations depending on the environment?
Absolutely. Biogeochemical cycles, they operate differently in different ecosystems because of variations in climate, soil types, vegetation, and other factors. For instance, in a tropical rainforest, with all that abundant rainfall and warm temperatures, nutrient cycling tends to be very rapid. Dead organic matter decomposes really quickly, releasing nutrients that are rapidly taken up by plants.
So it's like this high-speed nutrient expressway in the rainforest.
Exactly. But in contrast, in a desert ecosystem where water is scarce and temperatures fluctuate quite a bit, nutrient cycling is much slower. Decomposition rates are slower, and nutrients tend to be tightly held in the soil.
So it's more like a slow and steady nutrient savings account in the desert. It's fascinating how these cycles adapt to all these different environments.
And this highlights the importance of understanding the specific dynamics of biogeochemical cycles in different ecosystems. It's crucial for effective conservation efforts and sustainable resource management.
Yeah, that makes sense. You wouldn't apply the same approach to managing a rainforest as you would to managing a desert.
Precisely. Each ecosystem has its own unique characteristics and vulnerabilities, and managing them effectively requires a deep understanding of the underlying biogeochemical processes at play.
So it's not just about knowing what these cycles are. It's about understanding how they function in all these different contexts, and then applying that knowledge to make informed decisions.
Exactly. And that brings us to another crucial aspect of these cycles, their interconnectedness.
Okay, we talked about how different cycles interact, but how does this interconnectedness play out on a larger scale?
Well, for starters, remember how the water cycle connects different parts of the planet,
Yeah.
transporting nutrients, shaping landscapes.
Yes, it's like the circulatory system of the Earth.
Precisely. And this interconnectedness extends to other cycles as well. For instance, the carbon cycle and the nitrogen cycle are intimately linked. Nitrogen-fixing bacteria often rely on carbon compounds for energy, and the decomposition of organic matter releases both carbon and nitrogen.
So it's like these cycles are constantly exchanging resources and influencing each other's performance.
Exactly. And this interconnectedness creates this complex web of feedback loops. Changes in one cycle can ripple through the entire system, impacting other cycles and ultimately influencing the health and stability of the whole planet.
It's a powerful reminder of how interconnected everything is on Earth and how even seemingly isolated actions can have these far-reaching consequences.
And that brings us to the critical question. How are human activities impacting these delicate cycles?
Okay, let's dive into that. We've touched on some examples like fossil fuels and fertilizers, But what are some of the broader impacts?
Well, one of the most significant impacts is on the carbon cycle.
Huh.
As we talked about earlier, the burning of fossil fuels, deforestation, and other human activities, they've dramatically increased that concentration of carbon dioxide in the atmosphere, and that leads to climate change.
So we're basically overloading the carbon cycle with more carbon than it can handle.
Precisely, and all this excess carbon dioxide, it acts like this heat-trapping blanket you see, and that leads to a warming planet. And that comes with a whole cascade of consequences, things like rising sea levels, more extreme weather events, and even shifts in plant and animal communities.
Yeah, it's a pretty stark reminder of the power that we wield and the responsibility that comes with it. We also touched on how excess fertilizer use can disrupt the nitrogen cycle. Yeah. What are some other ways that we're impacting these cycles?
Well, our impact extends beyond carbon and nitrogen. For instance, deforestation not only disrupts the carbon cycle by removing trees, which, absorb carbon dioxide, but it also impacts the water cycle. It reduces transpiration, that's the release of water vapor from plants, and that can alter local rainfall patterns and even contribute to desertification.
So it's like this domino effect,
Hmm.
where one action can trigger this cascade of impacts across multiple cycles.
Exactly. And then there's pollution. Industrial activities release this whole cocktail of chemicals into the environment. And some of those chemicals can accumulate in organisms and disrupt biological processes. These pollutants can travel vast distances, through the atmosphere and water, contaminating ecosystems far from their source.
It's a pretty sobering reminder that we're all interconnected and that our actions have these far-reaching consequences. But it's not all doom and gloom, right? We can make choices to try and lessen our impact.
Absolutely. It's not about feeling powerless. It's about understanding these cycles and making informed choices that support their balance.
So what can we do? What are some tangible steps that we can take to make a difference?
Well, for starters, we can reduce our reliance on fossil fuels by transitioning to renewable energy sources, things like solar and wind power. We can also support sustainable agriculture practices that minimize fertilizer use and soil erosion. And we can all try to reduce our own consumption and waste, by choosing durable products repairing instead of replacing and composting food scraps.
So it sounds like it's going to take a combination of individual actions and systemic changes.
You're exactly right. We need to advocate for policies that promote sustainability. We need to invest in research and development of green technologies. And we need to shift our cultural values towards a greater appreciation for nature.
It's a call to action for all of us to become more conscious of our relationship with the planet and to participate in creating a more sustainable future.
Well said. And that brings us back to our initial point. These cycles are the foundation of life on Earth. They provide the air we breathe, the water we drink, the food we eat. They regulate our climate, and they even shape our landscapes.
It's amazing to think that something as simple as breathing connects us to this vast, intricate web of life.
And it's a reminder that even small actions can have ripple effects throughout these cycles. Every choice we make, every action we take is an opportunity to support the balance of these systems and create a healthier planet for ourselves and for generations to come.
It's a powerful message of interconnectedness, responsibility, and hope. Thank you for joining us on this deep dive into biogeochemical cycles. Remember, every breath you take, every bite of food you eat, is a testament to the intricate beauty and resilience of these extraordinary systems. Let's all strive to understand them, protect them, and live in harmony with them.
Well said. And as we wrap up this episode, I want to leave our listeners with a final thought. Take a moment to appreciate the wonder of these cycles. It's the silent symphony of elements flowing through the air, the water, the soil, and all the living organisms. Recognize the vital role that they play in sustaining life on Earth. And remember that we're all interconnected participants in this grand ongoing story.
Beautifully put. And to our listeners, don't forget to like, subscribe, and click that bell icon to stay tuned for more deep dives into all sorts of fascinating topics. Until next time, keep exploring, keep learning, and keep those minds curious.